So good morning and good evening, Juniper. Welcome to this new session of distinguished speaker of the J-Talk series. My name is Domenico, a member of our technical community, and I am extremely pleased to present Rob Hayes, who is the CEO of Atom Computing. Just to introduce briefly who is Rob, he is a recognized industry leader and founding of the board member of Ethernet Alliance, and is an executive sponsor of for creation of a Compute Access Link Consortium. And last but not least, is serving in a steering committee of OECD AI Compute Task Force. In his past tenure, Rob has held important and senior position in both Lenovo and Intel, where he met our CTO, Raj, and he'll probably chat a little bit how they come together. He has some interesting tips on this one. But introducing the title of the presentation, Introduction to Quantum Computing, it brings some memories back to my youth when I was studying computing and computer physics. And effectively, it is still about electron and holes. But Rob will help us to this new journey of quantum technology, where we will discover a more interesting and awesome world that will come from a new particle and new methodology on how they effectively are transforming this quantum technology, our world, and specifically what is the huge impact that this technology are having on the computing, which is exactly the quantum computer world. And so with any further ado, I would just welcome Rob on the stage, and please to you.
Thank you so much, Domenico. Pleased to be here, and thanks, Raj, for the invitation to join you guys today. I met Raj, it's probably been maybe 15 years or so, when I was at Intel, and he was a fairly senior executive as an Intel fellow, and I was an individual contributor product manager at the time in our Ethernet division, and I was working on some remote management and security technologies that Raj had a particular interest in. So we became friends, and he became somewhat of an informal mentor to me at the time. And I later moved on in my career to be a vice president at Intel and lead the Xeon processor product line, as well as other Ethernet products and high performance compute fabrics as an executive there. And then I went to Lenovo as the chief strategy officer. And all through the way, Raj and I have kept in touch and found ways for our companies to collaborate wherever he's been or I've been. And so pleased to get to speak to the Juniper team here. And I do have a good mix of background in both computing technologies as server system vendor, as well as CPU provider, but also in networking, Ethernet products, IEEE standards, and other industry consortia. So I've kind of been at the crossroads of compute and networking through my career, and have enjoyed all of it. So right now I'm at Atom Computing. I joined Atom Computing, which is a startup quantum computing hardware provider, last year in July as the CEO. I actually got engaged with the company about 1.5 years ago as a board member and an advisor to the founder and then CEO, and really became enamored with both the technology and the market opportunity for quantum computing, as well as the technology that Atom Computing has created. So I'm gonna talk to you today a little bit about what is quantum computing, what are some of the different technologies that different companies and academic researchers and so forth are pursuing to bring quantum computing to life. I'll tell you a little bit more in depth about what we're doing at Atom Computing and why we think it's distinct and quite scalable. And then we'll talk about what people are going to do with quantum computers and how it might impact Juniper and everyone on the call here. And we'll open up for questions. So that's the agenda for today. And I'll get right into it. So Atom Computing is based in Berkeley, California. It was founded in 2018 by Ben Bloom, who is standing on my left to the right in the photo. I'm in the center. And Jonathan King, who is kind of over my right shoulder and over one. And so they both have PhDs in physics and chemistry, respectively, and are driving our quantum engineering teams as well as our applications teams, respectively. We're kind of known for being the fastest to deliver 100 qubits. A qubit, as we'll talk more about, is the fundamental building block of a quantum computer. And the number of qubits kind of dictates the size of the machine or the scale of the machine. And when we announced our 100 qubit system, which was completed last year, it was tied with Google's for the world's largest gate-based quantum computer. And we did it in only 2 years with $20 million raised at the time. So much faster and much cheaper than anyone else had done. And that's kind of a testament to the technology that we chose. Additionally, our qubits are very high quality. We've published technical papers that demonstrate world record coherence times, which is, we'll talk more about that, but that's how long a qubit holds the quantum state. And so that's very important for the performance of the computer. Quantum computing is one of these kind of once in a 50-year paradigm shift in computing performance. It is going to touch many applications and many industry verticals. We'll talk more about how it's different than classical computing, but at the end of the day, it won't replace classical computing. It'll supplement it in the same way like GPUs and FPGAs and accelerators accelerate workloads off of standard CPUs. Quantum computers will offload certain portions of workloads that are calculations that are amenable to quantum subsystems and really accelerate the performance of many applications. We'll talk more about that later. First of all, what is quantum computing, right? So classical computing, as everyone is aware, is we have bits, and bits can hold one state at any time, and it's either on or off, 0 or 1, or 1 or 0, right? So each bit holds a value of 0 or 1. In a quantum system, we have these things called qubits, which is just short for quantum bits. And they actually don't hold a 0 or a 1. They hold a they have a complex coefficient value. It's represented as a vector in three-dimensional space, often depicted as a sphere, is like what you see in the diagram here. But each qubit holds that one complex number, which has a lot more information in it than just a 1 or a 0 on or off. And when you string multiple bits or multiple qubits together, this is where the power of quantum computing really shines. So in a classical system, again, each bit holds a 0 or 1, and you can string, as many of them together as you want in your system. And you can hold one value, and that value can represent a number from 0 to 2 to the n minus 1, right? So you put these bits together, you get one larger number as you add more bits to it. In a quantum system, remember, we already have complex numbers held in each quantum bit, and we have a property called entanglement. And when you get multiple qubits together, they're able to what's called entangle, and that system can now hold 2 to the n values at the same time. So instead of one value from 0 to 2 to the n minus 1, you can hold 2 to the n values, which means that the performance and the power of these qubits grows exponentially with the system, which is where quantum computing gets its power from. To give you one example, so this is a Google example, a fairly famous paper they put out about a year or so ago, where they claimed quantum advantage on a given workload. It was a workload that is one that's well known in quantum computing to be something that quantum computers can do much faster than classical computers could do. And they demonstrated on their system, which is a 100 qubit system, that they can do the calculation in 4 minutes. And that calculation would be estimated to take about 10,000 years to perform on a classical computer. So that's an estimate. I don't know if it's exactly right or not, but you can see that we're talking orders and orders of magnitude different performance. And so I think that's really kind of a good example of why people are so interested in quantum computers, is because there's certain calculations that just aren't practical or cost effective to do on a classical system. So people just won't try them. But they can be done on quantum systems. And this is like modeling natural systems like fluid dynamics or chemistry, molecules, energy, and things like that are things that people are very interested in modeling on quantum systems. Another kind of comparison. So this is the Summit supercomputer at Oak Ridge National Lab. This is, right now, it's the second most powerful quantum computer in the world. As you guys probably all know, supercomputers are very large. This one is the size of 2 tennis courts. They're often the size of a full warehouse. This one consumes power of 10,000 homes, 185 miles of cables, 200 million cost for an Oak Ridge to buy this from IBM. And the performance that you're getting out of this is the equivalent performance of what you could get out of 50 to 60 logical qubits. A logical qubit is an error-corrected qubit. We'll talk a little bit more about that as well. But you can see that massive performance out of relatively small systems is the promise of quantum computers. But here's the problem. In order to get that power, we need to build large-scale quantum computers, meaning more and more qubits, and we need to do that with error correction. And error correction requires more physical qubits than what's called a logical qubit, because you need to sort of oversubscribe the system, because these qubits are prone to noise and can have a certain error rate. And in order to kind of mathematically cancel out that error rate, you need to kind of oversubscribe the number of physical qubits to logical qubits. And it turns out this isn't like a 10 to 5 ratio or 10 to 4 ratio or something like that. It's like hundreds to one, a kind of ratio to really be able to cancel out all the error corrections for very large circuits, or all the errors. And so there's multiple factors that go into the performance of a quantum computer. It's not just the size of the qubit, or sorry, the number of qubits in the system, but it's the error rate, like I just described. So people talk about fidelities. This is a very common thing for people to report, as they say I have 99% fidelity or 99.5% fidelity. That's simply 1 over error rate. So if you have 1 error out of every 100 calculations performed on a qubit, that's a 99% fidelity. And if you think about like a circuit depth, I'm going to run a series of calculations in order. If you ran 10 calculations in order and you got 1 error out of every 100, you would be 99.9 to the 10, or 99.99 to the 10, and that would actually be a pretty high probability of an error. So that's why we want to have error correction in there, and a low error rate to begin with. Also coherence. So these quantum systems, depending on what kind of technology you're using, are often kind of prone to falling out of what's called coherence, which means they lose their quantum state fairly quickly. Superconductors, which are the initial kind of quantum computer, have a very short coherence time. That's one of the downsides of them. They only can hold the information for microseconds, and then it's lost. And so if you lose the information while performing a calculation, then you have to start over. And it turns out with error correction, there's a feedback loop going on in the system where you're trying to detect and correct errors, and you need to hold that information for a long time. So short coherence means difficult error correction. Long coherence means lots of time to perform deep circuits and lots of time to perform error correction. So that's a very important metric. There's something people talk about as connectivity. Connectivity is qubits get entangled. I'll tell you, I have a little demo of that in a few minutes here, but basically you can have 2 qubits and they can interact with each other and share information during the calculation. And there's only certain qubits in a system that can connect with each other depending on the topology of the system. So in our system, for example, only nearest neighbor qubits in space, the ones that are literally like next door to the one that you're using, can connect to each other. Other systems, you can connect to qubits within a chip, but not across multiple chips and things like that. So all of that has some impact on performance. Error correction, do you have the ability to detect and correct errors? Can you do mid-circuit measurement where you can actually detect and correct as you're executing through a circuit, or you can only do it at the end? That will affect performance. And then finally, gate speed, or the clock cycle. And some gates or some qubits take longer to perform calculations than others. And so all that adds up to a multidimensional space kind of problem and trade-off space for performance in the system. I'm not going to talk about benchmarks today, but there's things called quantum volume and other benchmarks that try to take all of these things into account and give some kind of numerical representation of the overall performance of a system. But right now, what I was going to talk a little bit about is some of the different technologies, or what we call modalities in the industry for quantum computers. The first 2 quantum computing type systems, I should say I'm only talking about gate-based systems here. There's a type of system called an annealer, or a simulator. D-Wave is the most popular or kind of oldest company that's been building these. This is kind of a different form of quantum computing. It's useful, but it's only useful for a subset of applications, and it's not really the type of systems that most people are looking for the broad set of applications. So within the gate-based quantum computers, which is the kind of more broadly applicable type system, superconductors were the first technology to build qubits for these quantum computers. Google, IBM, and Rigetti are the three leaders in this space. Basically, what they do is they build chips using semiconductor manufacturing technology. These chips hold qubits in there. They can basically get the electrons into various states on these chips that represent the quantum states within a qubit. And they have to wire each chip up together, and so that they're all connected, so they can all operate as one system. And so you get these beautiful photos, like you see on the left here, of what IBM calls the golden chandelier. And that's just simply because you've got all these chips, and these chips have these gold wires connecting them so that they can interact with each other. They've been doing this for about a decade or more. The qubits are relatively high quality. They've gotten the noise out. They've got the manufacturing kind of dialed in. The problem is scaling with this. Every time you want to add a qubit, you have to add another wire. So this is a picture of a system with a few dozen qubits on the left. You can imagine if you got to like 10,000 or a million qubits, you'd have a million wires, literally, each of them sending an RF tone down to the qubit. And I don't know how you would wire up a million wires. That supercomputer we saw on the other page was probably I don't even know, 20 or 30,000 nodes probably. So that's, that 185 miles of cable was probably only going to 20 or 30,000 things, not a million things. So you can imagine the complexity. More recently, companies like IonQ, which went public last year, and Quantinuum, which was a recent merger between Honeywell Quantum Systems and Cambridge Quantum Computing out of the UK. They've been manufacturing these things called trapped ions. It's a different type of qubit technology. They make chips, but these chips have little like channels in them or voids, and they create magnetic fields in the voids, and then they load ions, which are just charged particles, into those voids, and they get kind of suspended in air. These systems also have to be wired up and connected together. Both of these types of systems have to be cryogenically refrigerated in dilution refrigerators. And as they get bigger, more wires, larger refrigerators, bigger and bigger engineering problems. So while both of these modalities have very high quality qubits and they've been around for a while, they're both very challenged to scale. And that kind of leads to what we're doing and what many others in the industry are doing. So there's a number of companies and academic institutions looking for a more scalable approach so that we can create many more qubits, because we ultimately need millions of qubits, right, in order to have a few thousand logical qubits and perform very large calculations. And so these are these aren't all of them. There's a couple others that are kind of more in the research phase, but these are the 7 kind of, probably most prominent alternatives to superconductors and trapped ions. We're pursuing neutral atoms. Sometimes they're called cold atoms. I'll tell you how it works, but in the 30-second version is we basically trap atoms in a vacuum chamber with lasers, and they get stuck in free space to that laser, so they're not moving at all. And if they're not moving, they're cold by definition. So that's why they're also called cold atoms. And we can manipulate the quantum states inside the atom's nucleus using other laser tones. Photonics is probably the second most promising of these scalable ones, or furthest along. There's a very quiet startup called Quantum that is pursuing this, and Xanadu out of, I think they're in Canada, is a little bit more vocal. But these are 2 companies, and they're basically using silicon photonics to get photons to act as qubits. There's a number of others here. You can still quantum dots that Intel's pursuing, silicon spin, and others. But these are all, they're all different approaches, all different technologies, different ways of manufacturing systems, but all going after more scale, because people generally see that superconductors and trapped ions will hit some kind of a scaling wall, in the not too distant future. So to dive in a little bit more into the neutral atoms and how that works and what we're doing at atom computing. So neutral atoms are simply atoms in the second column of the periodic table. They're alkaline earth metals. They have what's called a closed shell. They're also called neutral because it basically means they have the same amount of protons and electrons, which basically means that they don't interact with anything in the environment. They're just very stable. And that stability is what gives them their long coherence times. We're able to use the nucleus of that atom to create spin. Remember, if I showed you represent the the coefficient inside a qubit with a sphere, well, we can actually literally rotate the nucleus of the atom to be in wherever we want in space. I'll show you a demo of how we trap them with optical tweezers, but what's really beneficial about this is that these atoms can be very close together. We in our system keep them about 4 microns apart, and we trap them in a grid, and you can actually see. Looks like my little GIF animation's not working on this one, but usually that little diagram in the bottom right is kind of moving, and you can see the atoms turning on and off as we're running the system. But basically, we trap these atoms in an array. They're 4 microns apart. Our current system's 100 qubits, so it's 10 by 10. And so that whole, all 100 qubits fit in 36 microns on a side, right? And when we get to 1 million qubits, we'll be in a 3D array, 100 by 100 by 100. That's 1 million, 4 microns apart. That's still less than half a millimeter on a side to get all 1 million qubits. So very, very small, very different than that golden chandelier that you saw from IBM and Google. And all of this is controlled wirelessly because we're doing it with lasers. And so instead of having to have a wire that goes to each atom, we just have a point of light that goes to each atom, and that's how we control them. So I'm going to show you kind of like a cartoon-like demo to try to make it maybe a little bit more clear what we're doing, and then we'll talk a little bit more about like what are you going to do with these quantum computers. So we basically have a system where, oh, this isn't working very well. Oh, my animation might not be working on. Okay, well, I'll just talk through it, and the animation may or not work. So we have atoms. The atoms are basically floating around in a vacuum chamber. There's nothing in there except for what we put into it, which is strontium in a gaseous form. And what we can shine a specific color of light on the atom, and it gets stuck in the focal point of that light, and it just freezes in space. It freezes to like 4 microkelvin. It's just so still, it doesn't move. Shoot, my animation's just not working. So let me, so we shine that beam of light, we capture the atoms. I'm just gonna try to get through this. But we don't just capture one, we capture many. So we captured in a grid of light. So we just have multiple points of light in a grid. The atoms are floating around. We capture them as they cross the beams of light. If we miss one, we can rearrange the atoms. We can just steer the beams of light over if we want. So what we actually have is a system that's a larger array than 10 by 10. And we capture some, something less than 100 or 100% of the atoms in there. And then we just rearrange it into a tight, fully populated grid to get entanglement. And then within the atom, we use the nucleus itself to create the qubit and the spin. Apologize, the animation's not working. We can create entanglement with what's called Rydberg states on these atoms. So normally the atoms, my fingers are kind of representing the electron cloud and the orbit around the nucleus. We can actually, with different colors of light, excite the atom so that the electrons cloud actually goes to a different orbital radius. And that can be calculated and measured. So that's it's something that we can control. And when they get into what's called the Rydberg state, the electron cloud is very large. And so these atoms that normally are quite far apart from each other, 4 microns, which is very far compared to the size of the atoms themselves, when they get into these Rydberg states, they're actually bigger than that 4 microns. So the energy between the electron clouds can interact with each other, and that's how we get entanglement. And then we can create what's called, there's a full gate set that's defined. It's, I think, 22 gates that are out there. And we can run single qubit gates, 2 qubit gates, and we can do all that in parallel. So this is just representing like the full array running different gates, which make up a circuit. And then at the end, we shine a flash of light on it, and we can read out the state of each qubit. And then we can shine another flash of light on it, and all of those qubits get reset to their ground state, and we can start over and run another circuit. So again, apologize the animation didn't work over Zoom for some reason, but that's kind of how it works. If you want to kind of see it from a system diagram perspective, this represents this blue box in the middle represents the vacuum chamber. It's got little windows in it. This is where the qubits are. We shine different colors of light into it via different different wavelengths of lasers. We control all that with a RF control system. Interestingly, it looks a lot like a cellular base station. It's a micro TCA chassis. It's got RF, line cards in it. We're running software-defined radio network over that, so we control everything with software, and we're just sending different tones of light or tones down the cables, the RF cables to the lasers to change the light pulses, and we're just controlling amplitude, phase, and frequency on that light in order to go do that and where it is in space. We read out with a camera. It's focused through a microscope objective, so it's a kind of a regular high-speed, high-resolution camera that's just focused through that microscope. So that's how we read out. And all of this goes back into a rack of standard servers that sits off to the side of the system that runs our software stack, which would be our scheduler, our operating system, our APIs, our storage, and all that kind of stuff. So that's kind of like logically what the system looks like. Physically, if you walked into our lab in Berkeley, this is it. So this system here is our first. It's a prototype. It's not a product. 100 qubits. It's 5 feet wide, 12 feet long. Most of it is an optical table that you see in the middle. Off to the right is the vacuum chamber with the glass cell and the microscope objectives that where the qubits reside. All that stuff in the middle that looks kind of complex is hand-placed optical acoustical devices, mirrors, prisms, things like that, little micro motors. And all of that is kind of hand-placed for maximum flexibility today for the prototype so that we could experiment and make changes at will. Moving forward, all of that stuff has been CAD designed and manufactured. So it's all kind of fixed to what we want it to be. So that takes the flexibility out, but it makes it much smaller, easier to reproduce, and higher quality, less error prone. So the ironic thing, as the system grows in size of qubits from 100 to 1,000 to 10,000 and beyond, the physical size of the system will shrink substantially because all of that hand-placed stuff goes away into little manufactured modules, basically. And this is, I guess, our version of the golden chandelier where the qubits sit. They're in a little glass cell, which is where the high vacuum is. It's 2 plates of glass with a frame around it. And it's high vacuum. The atoms are in there, and the lasers and the microscopes are sort of like fixed up against that. It's about the size of a silver dollar, to give you some perspective, and it won't change. It'll be that size all the way up through millions of qubits. So again, the size of the system the quantum part of the system right here will stay the same. The infrastructure will all get smaller, and the performance will go up. So kind of a little counterintuitive, but pretty cool. And that's why this technology is so interesting for scaling is that it, you don't have to worry about all these wires. This operates at room temperature, et cetera. And then here's just like a little kind of photo of like how do we see the system, right? We don't actually have people looking at it, computers are looking at it, but the system is just read out. And when we read it out, the atom is either glowing or not glowing to say what the answer was 0 or 1 for each individual qubit. And all the complex computation happens during the calculation, which is pretty interesting. Let's see. So what are we going to do with these computers? There's a lot of workloads that companies are starting to invest in, commercial workloads. I talk to like Fortune 500 companies pretty regularly: financial services, transportation, energy, pharma, biotech. And a lot of these companies already have quantum development teams. They've hired quantum physicists and computer science and data science professionals who've gotten some training in how do you program quantum computers or been trained on the job. And they're starting to invest in thinking about their workloads and how do they kind of evolve from maybe their current HPC workloads or their current, like Monte Carlo simulations and things like that, and take into account the capabilities of quantum computing. And so they're already starting to buy time on some of the systems that are out there from IBM or IonQ or D-Wave, and running experiments, learning how to program these systems and getting some feedback, while their application teams are starting to write, algorithms that can eventually run on quantum computers when they reach sufficient scale. Frankly, there's not a lot you can do with 100 qubits today from a commercial perspective. It's really around experimentation, and people are looking for, thousands and more qubits to be very, very useful for them once you take into account error correction. But these are some of the early use cases. So battery development, clean fertilizer traffic optimization, drug development. Artificial intelligence is a really interesting one. I feel like one of my slides got missing here, but there's actually 4 classes of workloads that people are looking at. Optimization problems. You're trying to optimize a portfolio, optimize multipath routing, like think packages coming from like a FedEx packages, got millions of packages coming from different addresses every day, going to different addresses, and they get picked up by trucks doing loops in neighborhoods and put onto bigger trucks and trains and planes, and then fan back out to trucks doing loops in neighborhoods. That's a multipath routing problem, and quantum computing is really good at that, or it will be really good at that when we can actually put the maps of sufficient scale into the system. And so you can imagine that you could do like a daily map optimization rather than having a fixed function sort of loop of these trucks and planes and stuff that could save time, money, fuel, and all that kind of stuff. So that's one example. Financial services like risk modeling and portfolio optimization is another one. Simulation's a big one. So simulating natural processes like molecules attaching to diseases for drug discovery and drug design is a good one, and things like that. Also, encryption and security is also a big one that gets a lot of probably more news than it should, but it is a big deal. And then machine learning optimizations is sort of another big category. So that's kind of my spiel on like what we're doing and what others are doing and how we're different, and some taste of what some of the early applications are. If Domenico asked me to kind of think about like, well, what does this mean for you at Juniper? And 2 things came to mind, and I'd invite Domenico to comment on this as after I sort of describe my thoughts here, and then we'll open it up for questions. So the first one that is kind of front of mind for me is hybrid compute architecture. So I think for about the last decade or so, hybrid compute architectures have become the norm or the standard, both in the cloud service providers as well as in like high performance computing in the enterprise. And what I mean by hybrid computing is that you just have different kinds of nodes, right? You have CPU only nodes that are maybe running the base application and the user interfaces and things like that. You've got GPU nodes that are running, vector processing workloads. You've got maybe some network optimized nodes that are running, security software or communicating with the outside world. And all of these things have sort of been put into a cluster, and there's some kind of a cluster controller and scheduler that steers the right workloads or portion of the workloads to the right nodes within these clusters, right? And I think, and this is just a kind of a photo I grabbed from Amazon that just kind of describes the current architecture, and I just tacked a quantum computer in there because honestly, I think that's how it's going to be. We will have quantum computers that get integrated in with these cloud services and or high performance compute clusters, and certain portions of workloads will be offloaded to that quantum system, and the results will be returned and integrated back in with the rest of the workflow. And from a Juniper perspective, you guys are both at the heart of how some of these things get connected together within a data center, as well as how data centers get connected to the internet and how data gets transferred, across the internet. And every time a new architecture gets introduced into one of these hybrid compute nodes, there's opportunity for network optimization for bandwidth, latency, quality service control, security, and all the rest of that. So I think it would be great if Juniper could think about how to integrate all of these different subsystems with quantum subsystems in the future to make sure that everything works well together and is secure. And then the other thought sort of on the right is quantum computing is great, and that's what my company is focused on and where my personal interest is, but there's other quantum physics applications, and sensing, networking, and communications, and encryption are the 3 probably biggest ones, and arguably will be deployed before quantum computing. Quantum sensing is already deployed to a large extent in the military for navigation for aircraft and submarines and ships. And that's probably the earliest market for global positioning systems and all that for quantum technologies. Quantum networking is another one, and this is how do you transfer information or states, quote unquote, instantaneously between 2 different places in the planet or in the solar system. And also, how do you connect quantum systems together? So maybe you don't have to convert from quantum to classical back to quantum, right? We can just stay in a quantum domain, and what performance or capabilities might that bring to the table? And then the third one there is encryption. And encryption, I think, applies to everything, all of the above in this space, including the classical computing. But you have to think about it both from an offensive and a defensive perspective. Most encryption protocols, as you guys are probably all aware, are based on, prime factor or, prime number factoring and things like that. And this is one thing that quantum computers are known to going to be really good at is how do you find all the how do you find all the prime factors of any given number, no matter how large the number is, right? So NIST is already working on new standards that they think are going to take a few years to roll out, that will be more defend against, the threat that quantum computers, pose to current, like SHA standards and things like that. But also, how can we use quantum computers to provide better encryption on the sort of offensive side?